Let us look at this question from Irodov and let us see 4 methods by which students do this question, and let us also see why in one of the methods the students make a silly mistake. Okay, so let us see the methods. Let us see, basically here the potential is given and the space charge distribution is asked in a spherical region. Okay, so let us see the first method. So method 1, the potential is given as AR square plus B. Okay, so E equal to minus dV by dr, which is equal to minus 2AR. Now, what students do is, intuitively they know that if E is some constant times R, it must be inside a uniformly charged sphere. Okay, so directly they write rho R by 3 epsilon naught equal to minus 2AR. Okay, and from this I get rho equal to minus 6A epsilon. So this is one method, intuitively how students do this question. Let us move on to the method 2. Okay, method 2, similar to this, you get E equal to minus 2AR, and after that you write Gauss law, minus 2AR into 4 pi R square equal to integral the charge enclosed. Charge enclosed is the rho as a function of R into 4 pi R square dr divided by epsilon. Now we can see that this side, there is R cube, and R square dr will give us R cube by 3, which means rho must be a constant. So what can I write here, tell me? I can write this as minus 2A R cube equal to rho is anyways a constant. Okay, rho R cube by 3 epsilon. So from here we get rho equal to, so this is the second method, no doubt in this method. Okay, let us move on to the third method. See, the first method only if it is a function of R. This one you can do, let us say if it is, this comes out to be some minus 2A R cube etc. The second method works out. Let us move on to the third method. In the method 3, we write rho equal to minus epsilon naught del square V. Okay, this is from a differential form of Gauss law. And what is V? Tell me. V equal to A R square plus B. Now I'll write it in Cartesian. So this will be A into x square plus y square plus z square plus B. The first step is to find the del bar V. Okay, this comes out to be 2ax I cap plus 2ay j cap plus 2az k cap. Okay, next again apply the differential to get del square V. So del square V is again differentiating this, we get 6a. Yeah, so we have del square V here, we put it here, and we again get rho equal to minus 6a epsilon. Okay, now let us move on to the fourth way where students do and make a silly mistake. So in the method 4, so again you write it like this, rho equal to minus epsilon del square V. Okay, now while finding out del bar V, so what do they get? Directly you differentiate this is a function. Okay, so you get minus 2, so del bar V is 2AR R cap. Okay, now when they do del square, they just differentiate this and they get 2A R cap. There is no, this is a scalar, del square V is a scalar. Okay, so you just get 2A, and when you put this again here, what do you get? Rho, tell me. You put this here, you get rho equal to minus 2A epsilon. Okay, this answer you get. What is rho? Minus 6 epsilon naught. Here you are getting minus 2 epsilon naught, which is not the correct answer. So what is the mistake that is going on in this method 4? Okay, let us see that. So let us look at the del operator. See, this is the del operator in the Cartesian coordinates, and this is the del operator in the spherical coordinates. So this is in terms of r, theta and phi. Once we know the relation, you can derive this from this easily. Okay. So the first thing is gradient. See this gradient of a scalar. Okay, E bar equals to minus del bar V. We were given a function in spherical coordinates here. So when you are finding electric field, you see here, you did dou f by dou x I cap, you got this to be correct. Okay, you converted first into Cartesian coordinates, and when you applied this, it is completely fine. Suppose in spherical coordinates you are applying, you see these terms, this dou f by dou theta, this is not there. There is no variation of theta. There is no variation of phi, so these all are not there. And this comes out to be correct. Directly you get minus 2ar here, and you get the similar thing here. Let us go to the next part, divergence of the vector. That is when we are finding del bar dot E bar. Okay, you see here again the definition here is the same, just dou x by dou x plus dou y by dou y plus dou z by dou z. But if you are in the spherical coordinate system, you directly cannot just do dou f by dou r here. Okay, see here whatever you are doing here, dou f by dou x I cap, dou x by dou x is similar. Here when you are doing gradient, you are doing dou f by dou r cap. But you see here, what is it, this part? We don't need to focus on these terms because we don't have theta and phi, so just ignore these two terms. Just focus only on this term. Okay, so when we are doing divergence, we need to use this one. We can't just differentiate. So what did we get? We got E bar equal to minus 2a r cap. Okay, we can't just say this is differentiation. We have to apply this. So what is del bar E? Del bar dot E bar equal to 1 by r square. Okay, dou by dou r of r square into ar. R square into ar is what? Minus 2a. Okay, so what will this be? Minus 3ar square. And if you differentiate it, what will you get? Minus 3a r cube, minus 2a r cube. If you differentiate it, you will get minus 6a r square divided by r square. So you get this as minus 6. So understood all of you? And yes, when you find out this is equal to rho by epsilon naught, you will get rho equal to minus 6a epsilon naught. So the fundamental mistake that the students make is, while calculating the divergence, the formula is not same in Cartesian and in spherical. So be careful. Try to do it in Cartesian, but if you have to do it in spherical, if you want to do it in spherical, just remember this formula while calculating divergence. It is pretty simple. Dou by dou r of whatever is the r term, just here r square and inside r square. A way to remember it. Okay.